Our fastest spacecraft, the Parker Solar Probe, travels at 394,000 miles per hour. That's 686 times faster than a commercial airliner. Fast enough to circle the entire Earth in under 4 minutes. And at that speed, traveling just 1 light year would take over 1,600 years. 1 light year? Not to another galaxy, not even to another star. Just 1 light year, and the best thing we've ever built would need longer than the entire span of recorded Western civilization to get there. But here's where it gets interesting, because with technology being seriously developed right now, that same crossing could take 5 years, and with concepts sitting at the edge of theoretical physics, it could happen in hours. In this video, we are going to work through every tier of technology, from the spacecraft we've already launched, to the propulsion systems being designed today, to the ideas that live at the boundary of what physics currently allows, and answer honestly, how long would it really take to travel 1 light year? If you're new here and you're into deep space science, hit subscribe and turn on notifications. We cover this kind of thing every week. Now, let's get into it. What a light year actually is. Most people know in a general sense that a light year is a measure of distance rather than time. But knowing that fact and truly feeling the scale of it are two completely different things, and the scale matters here more than in almost any other scientific topic you're likely to encounter. The numbers involved in interstellar distances are so far outside everyday human experience that the usual mental shortcuts, comparing things to football fields, or the distance from New York to Los Angeles, or the height of Mount Everest, simply fail. The scale is in a different category, so let's build it from the bottom up and see if we can get a genuine sense of what we're dealing with. Light travels at 186,282 miles per second. In 1 second, a photon covers a distance roughly equivalent to 7.5 laps around the entire circumference of the Earth. That's not a figure you can intuitively feel. It's too fast. The human brain doesn't really have a category for it. What we can do is anchor it against things we understand and let the numbers do the work from there. At that speed, light takes about 1.3 seconds to travel from the Earth to the Moon. It takes 8 minutes and 20 seconds to travel from the Sun to the Earth, which means the sunlight warming your skin right now left its source before most people finish their morning coffee. It takes about 43 minutes to reach Jupiter, about 82 minutes to reach Saturn, and roughly 5.5 hours to reach the edge of our solar system near the orbit of Neptune. A light year is what you get when you let light travel at that speed for an entire year, all 365 days, every hour, every second, without pause. The result is approximately 5.88 trillion miles, or 9.46 trillion kilometers. Written out numerically, that's 5,880 billion miles. The number has 12 digits in it. To put that in some kind of relatable frame, the distance from Earth to the Moon is about 239,000 miles. You'd need to stack roughly 24.6 million of those moon distances end to end to cover 1 light year. The distance from Earth to the Sun, about 93 million miles, fits into a light year about 63,000 times over. If you try to drive 1 light year at highway speeds, setting the cruise control at 65 miles per hour and never stopping for fuel or sleep, it would take you roughly 103 million years to arrive. The last time that much time elapsed on Earth, the first dinosaurs were just beginning to evolve. The continents looked nothing like they do today. The Atlantic Ocean was a fraction of its current size, and here's the figure that tends to land hardest for people. Voyager 1, the most distant human-made object in existence, launched in 1977 and has been traveling through space for nearly 50 years. In that time, it has covered just over 15 billion miles, and it is still traveling at about 38,000 miles per hour. By every earthly measure, Voyager 1 is extraordinarily far from home. By interstellar standards, it has barely moved. After half a century of continuous flight, it has covered less than 3,000ths of 1% of a single light year. That's the gap we're working with. In the context of interstellar distances, half a century of spaceflight is a rounding error. It's also worth noting what interstellar space actually means in this context. Voyager 1 crossed what scientists call the heliopause in 2012, the boundary where the solar wind, the stream of charged particles constantly flowing outward from the Sun, gives way to the interstellar medium. This was celebrated as a historic milestone, and it was. Voyager 1 became the first human-made object to enter the space between stars, but the heliopause is at roughly 120 astronomical units from the Sun, about 11 billion miles. 1 light year is 63,241 astronomical units. Voyager 1 is less than 0.2% of 1 light year from the Sun. It is in interstellar space in the technical sense of that phrase, but it is nowhere near being between stars in any meaningful spatial sense. The nearest star, Proxima Centauri, is 270,000 astronomical units away. Voyager 1 has covered less than 1/2000th of that distance. It's also worth understanding where 1 light year actually puts you in our cosmic neighborhood, because the destination itself is interesting. If you were to travel exactly 1 light year outward from Earth, you wouldn't arrive at another star. You wouldn't even leave our solar system's sphere of gravitational influence. You'd find yourself somewhere inside the Oort cloud, the vast, diffuse shell of icy bodies that forms the outermost boundary of the Sun's territory. This region is almost entirely unstudied, partly because the objects within it are so dim and so distant that we can only detect them indirectly. We know the Oort cloud exists primarily because of the comets it occasionally sends our way. When a gravitational perturbation, perhaps a passing star or the tidal forces of the galaxy, nudges an Oort cloud object inward, it begins a long, slow fall toward the Sun that can take thousands of years. These become the long-period comets that occasionally appear in our sky, sometimes bright enough to be visible in daylight, trailing tails of gas and dust across millions of miles. Those comets began their journey from roughly 1 light year away. In a meaningful astronomical sense, 1 light year from Earth is still our backyard. The nearest star beyond our Sun, Proxima Centauri, sits at about 4.24 light years away. A single light year gets you roughly a quarter of the distance to our closest stellar neighbor. With that scale established, let's look at what we could actually do about it. The machines we've already built. The Parker Solar Probe, launched by NASA in August 2018, is the fastest human-made object ever built. Its mission is to study the Sun's outer atmosphere, and to do that, it makes a series of progressively closer passes around the star, using the Sun's gravity to accelerate further with each orbit. In September 2023, during one of these close approaches, it reached a peak speed of approximately 394,736 miles per hour, more than 686 times faster than a commercial airliner, fast enough to circle Earth in under 4 minutes. At that speed, traveling 1 light year would take roughly 1,600 years. That's approximately the time separating us from the fall of the Western Roman Empire. Think about how much has changed in 1,600 years. How many civilizations have risen and collapsed? How many languages have appeared and vanished? How unrecognizable the world of 400 CE would be to someone living today. A probe launched now at Parker Solar Probe speeds would arrive at its 1 light year destination at a point in the future so distant that we can't meaningfully imagine what human civilization would look like by then, or whether it would still exist in any recognizable form. The Parker Solar Probe represents the absolute best we have actually built and launched. Every other spacecraft in our history has been slower. The Saturn V, which carried human beings to the moon and remains one of the most powerful rockets ever constructed, had a peak speed of about 25,000 miles per hour, placing a light-year crossing at around 100,000 years, roughly the entire duration of our species' existence. The Space Shuttle operated at about 17,500 miles per hour in orbit, implying over 150,000 years to cover 1 light year. Voyager 1, which used Jupiter and Saturn's gravity to slingshot itself onto an escape trajectory, travels at 38,000 miles per hour and would need about 17,500 years. The Helios 2 solar probe, which briefly hit 157,000 miles per hour during a gravitational swing around the Sun in 1976, still faces a 4,000-year crossing. The historical comparisons help put these figures in context. If the Parker Solar Probe had been launched when the Great Pyramid of Giza was completed, around 2600 BCE, it would still be in transit today, with over 3,300 years of travel time still ahead of it. The entire span of written human history, from the first Sumerian clay tablets to the present, would not be enough time. Go further back to when our species first emerged as Homo sapiens, roughly 300,000 years ago. The probe would still have covered less than 20% of 1 light year. These aren't rhetorical points, they're an accurate statement of the scale of the problem. What makes this particularly challenging is that the difficulty isn't primarily engineering, it's physics. Chemical propulsion, which has powered every rocket humanity has ever launched, is constrained by a mathematical relationship formalized by Konstantin Tsiolkovsky in the early 20th century. The rocket equation describes a fundamental limit. To go faster, you need more fuel. More fuel adds mass. More mass requires more fuel to accelerate. And the relationship compounds against you as you push toward higher speeds. To reach even 1% of the speed of light using chemical propellant, a chemical rocket would need to be made almost entirely of fuel. The mass ratio becomes physically absurd before you get anywhere near interstellar velocities. Chemical propulsion got us to the moon. It got robotic probes to every planet in the solar system and beyond, but it has essentially reached its ceiling as a technology for deep space travel, and that ceiling is nowhere near what interstellar distances require. Bridging the gap demand something with a fundamentally different energy source and propulsion mechanism. It's worth pausing briefly to put the required improvement in perspective. To cross 1 light year in a single human lifetime of, say, 80 years, a spacecraft would need to travel at roughly 73.5 billion miles per hour, about 11% of the speed of light. Our current best, the Parker Solar Probe, travels at 394,736 miles per hour. The gap between where we are and where we need to be for a lifetime length crossing is a factor of about 186,000. That's not a challenge of incremental improvement. That's a challenge requiring a different kind of propulsion entirely. The good news, and this is genuinely good news, is that the physics of our universe doesn't seem to prohibit us from closing that gap. The energy is there in principle. The question is whether we can access it, convert it to thrust efficiently, and build the engineering systems to do so reliably. Several distinct approaches have been identified as plausible routes forward. Ion drives and the efficiency approach. The first serious alternative to chemical propulsion for deep space missions is ion propulsion, and it works on a completely different principle. Instead of burning a chemical reaction to generate thrust, an ion drive uses electric fields to accelerate charged particles, ions, to very high exhaust velocities and ejects them as a propulsive stream. The force produced at any given moment is tiny, typically measured in millinewtons, roughly the weight of a few paper clips. But ion drives can sustain that thrust continuously for months or even years because they're extraordinarily efficient with their propellant. The technology is not theoretical. NASA's Dawn spacecraft used ion propulsion to orbit both the asteroid Vesta and the dwarf planet Ceres, becoming the first spacecraft to orbit 2 extraterrestrial targets in sequence. Japan's Hayabusa and Hayabusa 2 missions used ion drives to navigate to and from asteroids, with Hayabusa 2 returning samples from asteroid Ryugu to Earth in 2020. The European Space Agency's Smart 1 probe used ion propulsion to spiral out from Earth to lunar orbit. This is operational, proven technology, not a concept paper. The key advantage of ion propulsion over chemical rockets is captured in a quantity called specific impulse, essentially a measure of how efficiently a system converts propellant mass into thrust. Chemical rockets achieve specific impulses of around 300 to 450 seconds. Advanced ion drives achieve 1,500 to 10,000 seconds. That factor of 10 to factor of 20 improvement in efficiency is what allows a relatively modest amount of propellant to produce meaningful acceleration over extended mission durations. An ion-propelled spacecraft burns fuel at a tiny fraction of the rate a chemical rocket does, which means it can keep accelerating for far longer before running dry. Over mission durations of months or years, current ion drives can push spacecraft to roughly 200,000 miles per hour, noticeably faster than Voyager 1, but still placing a light-year crossing at around 30,000 years. Next-generation plasma drives and Hall-effect thrusters under development are pushing exhaust velocities higher still. Some theoretical designs propose systems with exhaust velocities 10 to 20 times greater than current operational engines, and when paired with compact nuclear reactors, which could provide the electrical power ion drives need without depending on solar panels that become useless in deep space, the performance improves considerably. Even so, ion propulsion is not a technology that will take us to the stars. Its role is more nuanced. It makes the outer solar system accessible for robotic missions. It extends the operational range of spacecraft dramatically, and it's pushing the engineering and materials science knowledge base that more powerful future systems will build on. Consider it a bridge technology, real, useful, and pointed in the right direction, but not capable of crossing interstellar distances in any human timescale. Laser sails and the starshot concept. If ion propulsion represents the realistic near-term improvement, the laser-driven light sail represents something categorically more ambitious, and it deserves careful attention because the physics behind it is genuinely sound and active research is underway. The concept begins with solar sails, which use the gentle pressure of sunlight to generate thrust. This isn't science fiction, the Planetary Society's light sail. 2 operated successfully in Earth orbit between 2019 and 2022, demonstrating controlled solar sailing. Japan's Ikaros spacecraft used solar sail propulsion in deep space during its 2010 mission to Venus. The physical principle is well established. Photons have no mass, but they carry momentum, and when they reflect off a surface, they transfer a tiny impulse to it. A sail large enough, light enough, and positioned close enough to the sun can accumulate these impulses into meaningful thrust over time. The limitation for interstellar purposes is that sunlight weakens with distance. Beyond the outer solar system, there simply isn't enough photon pressure to accelerate anything to interstellar speeds. The sun's light is too diffuse and too weak by the time you reach the distances where you'd want to be going fast. What if, instead of sunlight, you used a focused laser? A laser doesn't spread out the way ambient light does. It can be pointed at a precise target and maintain intensity over long distances. If you made the laser powerful enough, you could use it to accelerate a very thin, very lightweight sail to a significant fraction of the speed of light. This is the basis of Breakthrough Starshot, announced in April 2016. The initiative proposed a ground-based laser array generating up to 100 gigawatts of power focused on an extremely thin reflective sail, roughly 4 meters across, attached to a gram-scale spacecraft called a nanocraft or starship. The complete spacecraft, cameras, power source, communications, laser, navigation sensors would weigh no more than a few grams, roughly the mass of a paperclip. The laser array would fire for approximately 10 minutes. In those 10 minutes, the photon pressure from 100 gigawatts of focused light would accelerate the nanocraft to about 20% of the speed of light, or roughly 134 million miles per hour. At 20% of light speed, 1 light year takes 5 years to cross. The jump from our current capability, 1,600 years with the Parker Solar Probe, to 5 years with a laser sail represents a compression factor of over 300. It's genuinely difficult to overstate how dramatic that improvement would be. Breakthrough Starshot's original target was Proxima Centauri, 4.24 light-years away, reachable in about 20 years at that speed. The returning data signal would take about 4 years to arrive at Earth, making the total mission timeline from launch to data receipt around 24 years within a single human career. The engineering challenges are substantial. and the project's founders acknowledged this openly, identifying around 30 major technical problems at the initiative's founding. The sail material must be thin enough to respond to light pressure. We're talking about a thickness of hundreds of nanometers, far less than the width of a human hair, but robust enough to survive 100 gigawatts of focused laser energy without heating up and vaporizing. Researchers have been working on graphene-based metamaterials and other nanoscale architectures for this purpose. In 2025, a team from Brown University and TU Delft published work on an AI-optimized sail design just 200 nanometers thick with billions of microscopic perforations that reduce mass while maintaining high reflectivity. Keeping 100 gigawatts of laser power focused on a 4-meter target that is rapidly accelerating away, initially over vast distances on Earth, eventually over distances of light minutes, would require an optical array potentially kilometers wide, probably space-based, to avoid atmospheric interference with beam quality. And at 20% of light speed, the interstellar medium, that near vacuum of 1 atom per cubic centimeter, becomes a meaningful hazard, with each particle of dust hitting the spacecraft with significant energy. The nanocraft would need some form of shielding on its leading face. There's also no mechanism for deceleration. A nanocraft propelled to 20% of light speed by a laser would pass through the Proxima Centauri system in a matter of hours, capturing images and data in a brief flyby window before moving on into deep space permanently. It's a one-way flyby, not an orbital mission. Breakthrough Starshot's organizational momentum slowed in the years after its founding, and funding and leadership challenges have affected its pace. But the underlying research it generated has moved the field forward meaningfully in sail materials, miniaturized spacecraft, high-power laser systems, and interstellar communication. Other researchers and institutions have picked up threads of the work. The concept itself has generated a substantial body of peer-reviewed literature, with papers on sail geometry optimization, beam riding stability, communication systems for gram-scale spacecraft, and target system characterization. The mission design itself raises interesting questions about what such a probe would actually do during its brief window at the target. Flying through the Proxima Centauri system at 20% of light speed, the spacecraft would spend only a few hours within a useful observational range of the system's planets before screaming past and continuing into deep space forever. During those hours, it would need to operate autonomously, capturing images, measuring magnetic fields, analyzing any atmospheric signatures of Proxima Centauri b and other planets, and storing that data on board. Then it would activate its laser communicator and begin the decades-long task of beaming that data home, a signal that would take 4.24 years to arrive at Earth, even traveling at light speed. The miniaturized instruments required for this, cameras, spectrometers, magnetometers, power supplies, laser transmitters, all packed into a few grams, represent a separate engineering challenge from the sail and propulsion system. But the trajectory of miniaturization in electronics gives reason for optimism. The processing power of today's smartphones would have seemed impossible to engineers in the 1970s. The miniaturization required for a Starship-scale science instrument package is ambitious, but not categorically beyond what technology trends suggest is achievable within decades. The physics remains valid. If even half of the target velocity were achieved, 10% of light speed instead of 20, a 1 light-year crossing would take 10 years, and Proxima Centauri would be reachable in around 45 years. That's still a transformative capability compared to anything we currently have, and it represents a realistic target for this century if the necessary research investment is sustained. Nuclear propulsion, the road we chose not to take. There is a pathway to interstellar class speeds that has been seriously studied, partially tested, and then largely set aside. Not because the physics was shown to be wrong, but primarily because of political decisions made in the early 1960s. It involves nuclear energy in its most direct and powerful form, and it remains one of the most physically credible routes to meaningful interstellar velocities. In the late 1950s, a team at General Atomics in San Diego, which included veterans of the Manhattan Project, among them physicist Freeman Dyson, worked on a concept called Project Orion. The idea was direct to the point of being almost audacious. Build a large spacecraft with a heavily reinforced plate mounted at its rear. Detonate a sequence of small nuclear devices behind that plate at regular intervals. Use the pressure waves from each detonation to push the ship forward, with the plate absorbing the force through a system of shock absorbers and transferring it to the spacecraft as thrust. The mathematics of this approach were compelling. Each nuclear detonation releases energy on a scale that chemical combustion simply cannot approach. And even a modest conversion of that energy into thrust would produce spacecraft performance far beyond anything chemically possible. Early Orion design studies projected cruise speeds of 3 to 11% of the speed of light for fission-powered versions, with fusion-powered designs potentially going higher. At 5% of light speed, 1 light-year takes 20 years to cross. At 10%, about 10 years. These are numbers that transform the question of interstellar travel from a civilizational timescale problem into something at least theoretically manageable within a single human career. Project Orion was not killed by engineering failure. It was killed by the Limited Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, the atmosphere, and underwater. Without the ability to test and develop the propulsion system, the program lost its funding rationale and was shut down. The physics that underpinned it was never challenged. Dyson himself wrote about Orion for the rest of his career with a sense of genuine loss about what might have been. The Orion concept found successors in later design studies. Between 1973 and 1978, the British Interplanetary Society ran Project Daedalus, a detailed engineering study of an unmanned fusion pulse spacecraft designed to reach Barnard's star about 5.9 light-years away in approximately 50 years. Daedalus wasn't a vague concept, but a thorough engineering analysis. It specified propellant type, tankage, engine configuration, payload mass, and mission timeline. The vehicle would use pellets of deuterium and helium-3 compressed and ignited by electron beams, generating fusion pulses at a rate of about 250 per second to produce continuous thrust. Cruising at around 12% of light speed, it would cross 1 light-year in roughly 8 years. Project Longshot, a later study conducted jointly by NASA and the US Naval Academy in the late 1980s, proposed a nuclear fission spacecraft capable of reaching the Alpha Centauri system in about 100 years, implying roughly 4.5% of light speed, or about 22 years per light year. The consistent picture across all of these studies is that nuclear propulsion, whether fission or fusion, can plausibly deliver speeds between 5 and 15% of light speed. That range puts a 1 light-year journey somewhere between 7 and 20 years. These aren't comfortable numbers, but they're numbers that begin to feel like missions rather than geological epochs. A mission with a crossing time of 10 years can be planned, funded, staffed, and executed within a political and institutional timescale that human organizations can sustain. Geological epoch timescales cannot. The engineering challenges are severe but specific. Building nuclear pulse propulsion at interstellar scales requires a reliable supply of nuclear fuel. Project Daedalus specified deuterium and helium-3, with helium-3 being relatively rare on Earth but potentially abundant on the Moon and the gas giants. Managing the thermal environment aboard a spacecraft that is essentially riding a sequence of nuclear explosions requires engineering at the limits of known materials science. Ensuring that the system remains operational and controllable for years or decades of continuous operation far beyond any possibility of repair from Earth is a reliability challenge that dwarfs anything in the history of spacecraft design. These are not small problems, but they are engineering problems. They are the kind of challenges that yield to sustained effort, incremental improvement, and iterative design. The same kind of problems that were solved to build nuclear submarines, nuclear power plants, and long-duration deep space probes. The physics, unlike many other aspects of the interstellar travel challenge, is well understood and clearly supportive. Fusion power on Earth is advancing. The National Ignition Facility achieved ignition, more fusion energy output than laser energy input, for the first time in December 2022. And multiple commercial fusion ventures, including Commonwealth Fusion Systems and Helion Energy, are pursuing compact reactor designs with timelines measured in years rather than decades. If sustained fusion power becomes an operating technology within the next 30 to 50 years, as increasing numbers of researchers now believe is achievable, nuclear pulse propulsion for spacecraft moves from a paper study to a near-term engineering program. It remains one of the most credible paths available to us, and one of the most underappreciated given how seriously and thoroughly it has been studied. Antimatter, the most efficient fuel imaginable. Moving further along the spectrum of propulsion concepts, antimatter represents the theoretical ceiling of what conventional physics permits. The concept sounds exotic, but the underlying physics is well established and experimentally verified. We produce antimatter routinely in particle physics facilities around the world. Every particle of ordinary matter has an antimatter counterpart. The electron has the positron. The proton has the antiproton. These antimatter particles are identical to their matter counterparts in mass, but opposite in charge. When a matter particle meets its antimatter equivalent, both are completely annihilated, and their combined mass is converted entirely to energy. Not partially, entirely. This 100% mass-to-energy conversion is what makes antimatter so extraordinary as a theoretical propellant. The physics principle at work is Einstein's famous E equals mc squared, where E is energy, m is mass, and c is the speed of light. The c² factor is an enormous number, the speed of light squared, which means that even a tiny mass converts into a huge amount of energy when fully annihilated. A single gram of antimatter meeting a gram of ordinary matter releases energy equivalent to roughly 43 kilotons of TNT, comparable to the nuclear weapons used at the end of World War II, from 2 grams of combined material. For comparison, nuclear fission, the process that powers atomic bombs and nuclear reactors, converts about 0.1% of its fuel mass into energy. Fusion, the process that powers stars and hydrogen bombs, achieves roughly 0.3 to 0.7% efficiency. Chemical combustion converts a fraction of a percent of its fuel mass into energy, mostly through the relatively weak bonds broken and formed in combustion reactions. Antimatter annihilation converts 100%. It is the most energy-dense process that the known laws of physics permit. An antimatter propulsion system would direct the products of matter-antimatter annihilation, high-energy gamma rays, and other particles through magnetic nozzles to generate thrust. Theoretical analysis suggests that a well-designed antimatter drive could accelerate a spacecraft to somewhere between 50 and 80% of the speed of light. At 50% light speed, a 1 light-year crossing takes 2 years. At 80%, about a year and 3 months. These are numbers that don't just make interstellar travel conceivable, they make it feel genuinely achievable in human terms, at least for relatively small spacecraft. The obstacle is manufacturing. The total global production of antimatter across all particle physics facilities in the world, including the Large Hadron Collider at CERN, amounts to a few nanograms per year. A nanogram is 1/billionth of a gram. An antimatter-powered interstellar spacecraft would likely require kilograms of the material, hundreds of billions of times more than we currently produce annually. Beyond the production quantity, the production efficiency is deeply problematic. Creating antimatter in particle accelerators currently requires far more energy than the antimatter contains. The process is extraordinarily energy negative. You put in vastly more energy than you get out, which defeats the purpose of using antimatter as a fuel source. There are theoretical proposals for more efficient antimatter production methods. Using intense laser pulses to produce electron-positron pairs from photons, or configurations of particle beams that might improve efficiency, but they remain speculative and far from demonstrated. None of them address the scale problem in any near-term sense. There's also the containment problem, which is entirely separate from production. Antimatter cannot touch ordinary matter without annihilating. Storing it requires keeping it suspended in magnetic fields, never touching any physical container wall for the duration of the mission. The longest anyone has managed to trap and hold antihydrogen atoms, the simplest form of antimatter that could be relevant for fuel, is measured in minutes at current facilities. Storing grams or kilograms of antimatter for years in a spacecraft environment with no active maintenance from Earth represents an engineering challenge without precedent. What antimatter represents, practically, is a propulsion option that would be genuinely transformative if the production and storage problems were solved. And those problems are so extreme that no realistic roadmap for solving them currently exists. It is the clearest example in the propulsion literature of a technology that is physically permitted and physically compelling, but practically inaccessible at any scale that matters to us today. It defines the upper bound of what chemistry and conventional physics can offer, and leaves us hoping that the engineering will follow the physics eventually. Where physics gets strange, warp drives and wormholes, everything so far has operated within one important constraint: that matter cannot travel through space faster than light. Einstein's special theory of relativity establishes this as a fundamental physical law, and nothing in the century of experimental physics since then has challenged it. But there's a subtlety in what the theory actually says that opens a door most people don't know exists. Special relativity forbids matter from moving through space faster than light. What it doesn't address is the speed at which space itself can change, and we know from observation that space can move remarkably fast. The universe has been expanding since the Big Bang, and distant galaxies are receding from us at effective rates that exceed the speed of light, not because those galaxies are moving through space faster than light, but because the space between us and them is stretching. The fabric of space-time is expanding, and the galaxies are embedded in it. They're not breaking any cosmic speed limit. The medium they're sitting in is simply getting larger. In 1994, a Mexican physicist named Miguel Alcubierre took this observation and asked what became a famous question in theoretical physics. If space can expand and contract, could you engineer a localized region of space-time to do exactly that around a spacecraft? The answer he published was the Alcubierre metric, now commonly called the Alcubierre drive, or in popular terminology, the warp drive. The mechanism works by surrounding a spacecraft with a bubble of undistorted space-time. In front of the bubble, space is compressed. Behind it, space expands. The bubble and the spacecraft inside is carried along like a piece of driftwood on a current. The spacecraft never moves relative to the space inside its bubble, which means it never locally exceeds the speed of light. But the bubble itself moves through space at whatever speed the distortion is engineered to produce, including faster than light. It's not a violation of special relativity. It's a use of the geometry of space-time that special relativity doesn't prohibit. Alcubierre has been candid about where the inspiration came from. It was Star Trek. He was asking whether the science fiction concept of warp drive had a mathematical basis in real physics. The surprising and genuinely interesting answer was that it did, at least on paper. The complication, and it's a severe one, is the energy requirement. To create and sustain the warp bubble requires a form of matter with negative mass energy density, something called exotic matter, which would curve space-time in the opposite direction from ordinary matter. In Alcubierre's original 1994 paper, the amount of exotic matter required to produce a bubble large enough to enclose a spacecraft was approximately equal to the total mass energy content of the entire observable universe. The number is so large it's essentially a way of saying physically impossible. Subsequent research has found that by changing the geometry of the bubble, making it thinner, configuring it differently, the exotic matter requirement could be reduced significantly, though it remained enormous by any practical standard. In 2021, physicist Eric Lentz published research suggesting that warp drive-like solutions might be achievable using only ordinary positive energy matter, without requiring exotic matter at all. The physics community received this with cautious interest and ongoing scrutiny. and the work hasn't been widely accepted as definitively solving the exotic matter problem, but it points toward continued theoretical progress. The deeper problem is that exotic matter with negative mass energy density has never been observed. We don't know if it exists in the forms required. We don't know how to produce it if it does. And without it, the warp drive as originally formulated cannot be built. What the Alcubierre drive represents is a genuine mathematical framework for faster-than-light travel that doesn't violate known physics, but that requires materials and energy configurations we cannot access and may never be able to access. If it worked, crossing 1 light-year would take hours or possibly minutes, depending on how fast the warp bubble was configured to move. The Oort cloud and beyond would be a day trip. The nearest star system would be reachable in an afternoon, but we are nowhere near being able to build one, and whether we ever will be depends on physics questions that remain unresolved. The field of warp drive physics has attracted more serious academic attention in recent years than most people realize. Harold White at NASA's Johnson Space Center spent several years working on experimental tests related to the Alcubierre metric, attempting to detect microscopic warp field effects using sensitive interferometry. The work was not vindicated experimentally. No warp effects were detected at measurable scales, but it reflected genuine scientific interest in the question from within an established space agency. More theoretically, the Lentz paper from 2021 remains in active debate. If its claims hold up to scrutiny, they would represent a meaningful softening of the exotic matter requirement that has always been the Alcubierre drive's most damning obstacle. The consensus view in physics is skeptical but not dismissive. The warp drive is not considered crackpot physics. It is considered a genuine theoretical construct with severe practical obstacles that may or may not be surmountable. Wormholes occupy a similar theoretical position. General relativity, Einstein's theory of gravity, which describes space-time curvature, mathematically permits the existence of what physicists call Einstein-Rosen bridges. Popularized as wormholes by the physicist John Wheeler in the 1950s, these are topological tunnels through space-time connecting two distant points. In principle, you enter one end and emerge at a point light years away in a fraction of a second. The physics doesn't forbid this any more than it forbids the Alcubierre drive. The practical challenges are the same. Keeping a wormhole open against gravitational collapse would require exotic matter. Additionally, traversable wormholes, if they existed, would likely enable travel backward in time, creating causality paradoxes that most physicists find deeply troubling. Stephen Hawking proposed his chronology protection conjecture precisely to address this. The idea that some deeper undiscovered physics conspires to prevent time travel, and by extension, probably wormholes, from being physically realizable. It remains a conjecture rather than a proven theorem, but it reflects a widely shared intuition that the universe probably doesn't allow this kind of shortcut. If either warp drives or wormholes proved constructible, the question of how long it takes to travel 1 light year would essentially dissolve into a question of engineering preference. But as of today, both concepts are mathematically legitimate, experimentally unverified, and practically beyond anything we can conceive of building. They represent the outer edge of what the universe might allow, not what it currently makes accessible to us. what the journey would actually do to the people on board. The propulsion problem gets most of the attention in these conversations, but there's a parallel challenge that deserves equal consideration, because it would remain significant even if a fast propulsion system were developed. The human body is not built for space. Astronauts aboard the International Space Station in low Earth orbit on missions lasting 6 months to a year experience bone density loss at roughly 1 to 2% per month in key weight-bearing areas. Their muscles atrophy in the absence of gravitational resistance. Their cardiovascular systems adapt to microgravity in ways that cause problems when they return to Earth. The heart actually shrinks slightly, since it no longer needs to pump blood upward against gravity, and readapting to a gravitational environment can take weeks. The immune system becomes dysregulated in ways that researchers are still working to fully characterize. Some astronauts develop a condition called spaceflight-associated neuroocular syndrome, in which fluid redistribution in the body increases intracranial pressure, potentially causing vision changes that in some cases persist after the mission ends. All of this happens in low Earth orbit, still within the protective shell of Earth's magnetic field. The ISS is shielded from the worst of deep space radiation by that field, as well as by the mass of Earth itself, blocking incoming radiation from below. In deep space, those protections disappear entirely. Beyond Earth's magnetosphere, the radiation environment is genuinely hostile. Galactic cosmic rays, high-energy particles produced by supernovae and other violent astrophysical processes across the galaxy, penetrate everything except very dense shielding. Solar particle events produced by eruptions on the Sun can deliver radiation doses in hours that would approach or exceed established safety limits. The Apollo astronauts, who spent only days beyond Earth's magnetic protection, reported seeing flashes of light even with their eyes closed. Cosmic ray particles passing directly through the visual cortex. Studies of the Apollo crew members in the decades after their missions found elevated rates of cardiovascular disease compared to astronauts who never left low Earth orbit, a finding researchers have tentatively linked to their cosmic ray exposure during the lunar missions. A multi-year voyage through interstellar space, even at the relatively optimistic speed of 5% of light speed, would expose crew members to accumulated radiation doses far beyond what current medicine considers safely manageable without extraordinary shielding. The engineering response to this is straightforward in concept and deeply difficult in practice. You put mass between the crew and the incoming radiation. Hydrogen-rich materials like water or polyethylene are particularly effective at absorbing the secondary particles produced when cosmic rays interact with spacecraft structure. But mass is the enemy of fast travel. Every kilogram of shielding you add requires more energy to accelerate, which requires a bigger propulsion system, which requires more mass, which requires more shielding. The problem compounds. One approach researchers have explored is magnetic shielding, creating a superconducting magnetic field around the spacecraft that deflects charged particles before they reach the hull, similar to the way Earth's magnetic field deflects the solar wind. The concept is physically sound, and superconducting magnets can be made quite light relative to the protection they provide. The practical challenges include maintaining superconducting systems reliably for years or decades in deep space, generating the power needed to sustain a field, and the fact that neutral cosmic ray particles, which carry no charge, wouldn't be deflected by magnetic fields regardless. Magnetic shielding is a partial solution at best, though even partial solutions matter when accumulated radiation dose is the concern. The psychological dimension of a long interstellar voyage is harder to quantify, but no less real. The most isolated any human beings have ever been from their species is a communications delay of about 1.3 seconds experienced by the Apollo 13 crew at their maximum distance from Earth. Astronauts aboard the ISS speak with mission control multiple times per day, receive personal messages from family, and conduct live interviews with journalists and school children. They are alone in space, but deeply embedded in a web of ongoing human contact. On a mission traveling at 5% of light speed and crossing 1 light year, messages from Earth would take roughly 20 years to arrive. The crew would be making every decision, managing every emergency, celebrating every milestone, and enduring every difficulty in complete isolation, not the isolation of a remote research station on Earth, where resupply and evacuation are theoretically possible, but the isolation of a vessel that cannot return on any human timescale, cannot be reached, and cannot receive meaningful support from anyone. A crew member who became seriously ill or mentally unwell would be managed entirely by the resources aboard the ship. Research on long-duration isolation, from Antarctic overwinter cruise, from submarine patrols, from Mars mission simulations conducted by space agencies, identifies a consistent set of psychological challenges. Interpersonal conflict that tends to intensify over time as minor irritations become magnified in a sealed environment, depression, sleep disruption, cognitive changes, decreased motivation, and what psychologists call the third quarter effect, a well-documented dip in morale and performance that tends to occur in the final phase of any long, demanding mission. An interstellar voyage would represent orders of magnitude more extreme isolation than anything studied so far. The psychological architecture required to survive it, in crew selection, mission design, onboard support systems, and interpersonal dynamics, constitutes a genuine research frontier that has barely been explored. Some mission designers have tried to address the duration problem through the concept of multi-generational ships, self-contained communities traveling through space over multiple human lifetimes, with the descendants of the original crew eventually arriving at the destination. The idea has genuine appeal in engineering terms. It removes the need for any single individual to survive the full journey. But it creates problems that engineering can't solve. People born aboard the ship never chose to be on it. They would be born into a total environment they didn't consent to, with a mission they didn't volunteer for. Asking future generations to accept the purpose and terms of a mission their ancestors agreed to is philosophically fraught, and history provides no examples of a complex technical organization maintaining coherent purpose and capability across multiple generations without institutional breakdown of some kind. One partial solution that has received real scientific attention is medically induced hibernation. NASA has funded research into a state called torpor, a deep reduction in metabolic activity, similar in principle to but more extreme than the winter hibernation of bears or ground squirrels. The specific challenge is that human beings don't naturally hibernate. Our physiology doesn't have the mechanisms that hibernating animals use to protect cells from the damage that low temperatures and reduced metabolism would otherwise cause. Engineering those mechanisms, or finding pharmaceutical or other means to achieve a similar protective metabolic state, is a genuine biological research challenge. Some of the most relevant work is coming from research on hypothermic therapy in medicine, where patients are deliberately cooled to reduce brain damage during cardiac surgery or after certain injuries. Understanding how to extend the protective effects of cooling from hours to months or years would be a significant advance. If hibernation became reliably achievable for space missions, it would dramatically change the calculus of long voyages. A crew traveling for 20 years at 5% of light speed might spend most of that time in a torpor state, waking periodically for maintenance checks and health monitoring. The subjective experience of the journey would be compressed from 2 decades to perhaps a few months of waking time. The psychological burden would be reduced considerably. The physiological effects of microgravity and radiation would need separate solutions, but removing the burden of conscious isolation over years would be a meaningful improvement to mission survivability. What all of this illustrates is that interstellar travel is not one problem, but a family of problems that have to be solved together. The propulsion system that can cross a light year in 20 years is only useful if the people aboard can survive 20 years in deep space, which requires solving radiation shielding, microgravity physiology, life support reliability, food production, and psychology simultaneously. Solving any one of these in isolation isn't enough. They have to work together at the same level of reliability for the full duration of the mission. That's a harder challenge than it sounds, and it's one reason why mission designers who think seriously about human interstellar travel tend to be considerably more cautious about timelines than those who focus purely on propulsion. Time dilation, the universe's strange compensation. There is one more dimension to this problem that changes the picture in a genuinely counterintuitive way. It's called time dilation, and it's not a hypothetical, it's a confirmed physical phenomenon with practical engineering implications that any serious discussion of interstellar travel has to account for. Einstein's special theory of relativity predicts, and experiments have confirmed, that time passes more slowly for objects in motion relative to stationary observers. This effect is not a perception or a consequence of communication delays. It's a real difference in the rate at which time elapses, baked into the fabric of space-time itself. Atomic clocks flown on high-speed aircraft run measurably slow compared to identical clocks left on the ground. GPS satellites which orbit Earth at high speeds must have their internal clocks corrected for relativistic time dilation. Without the correction, GPS accuracy would degrade by miles within a single day. These are not exotic laboratory results. They're engineering constraints built into technology billions of people use every day, at everyday speeds. Anything we achieve with cars, planes, or even rockets, the effect is too small to matter practically. The difference in elapsed time between a jet-setting traveler and someone who stayed home their entire life amounts to a tiny fraction of a second over a lifetime. But as you approach the speed of light, the effect becomes significant and then extreme. A traveler moving at 10% of light speed ages about 0.5% more slowly than someone stationary, a real effect, though not life-changing. At 50% of light speed, the traveler ages at about 87% the rate of a stationary observer. What this means for interstellar travel is that very high speeds don't just get you to the destination faster in objective terms, they also compress how much time the crew actually experiences during the journey. A spacecraft traveling at 99% of light speed across a distance that takes 100 years from Earth's perspective would be experienced by the crew as a journey of about 14 years. The universe measures 100 years of elapsed time. The crew ages 14 years. Those are not the same thing, and the difference between them is real. For a 1 light-year crossing specifically, which takes just over a year from Earth's perspective at 99% light speed, the crew would experience only a few months of subjective travel time. The journey becomes, from the traveler's point of view, something that fits within the scope of ordinary human experience, even if it doesn't from Earth's frame of reference. The trade-off is a real and strange one. A crew that travels to a star 10 light-years away at 99% of light speed and returns would come back having aged about 3 years, while Earth has aged over 20 years. The people they knew before departure would be decades older or dead. The civilization they returned to would have changed in ways they couldn't have predicted. Time dilation makes the journey survivable from an individual lifespan perspective. It doesn't make it reversible in any human social sense. You go out for what feels like a few years and come back to a world that has moved on without you. Scale this up to more ambitious journeys and the effect becomes even more dramatic. A spacecraft at 99.9% of light speed could in principle travel hundreds of light years, while the crew ages only a few decades. From the perspective of the people aboard, the universe becomes accessible in a way it isn't from Earth's frame. But from Earth's perspective, those travelers left centuries ago. Any mission that exploits time dilation in this way is, in a fundamental sense, a one-way journey. Not one way in that the ship can't return, but one way in the sense that the world you return to is no longer the world you left. The energy required to reach these velocities is the insurmountable, near-term obstacle, but the physics is real. Time dilation is real, and the implications it carries, that interstellar travel over vast distances is not necessarily incompatible with human lifespans given enough energy, change the character of the long-term problem in an important way. The universe's geometry is harsh. Its physics, at least in this respect, offers a partial compensation. The view from inside. What the journey would actually look like. One thing that rarely gets discussed is what the experience of this journey would actually be, perceptually, because at different speeds, the universe looks genuinely different in ways that physics predicts precisely, and the qualitative difference between crossing a light year at 400,000 miles per hour versus 20% of light speed is far greater than the numbers alone convey. At the speeds of our current spacecraft, the experience of crossing interstellar space would be defined almost entirely by emptiness. The average density of matter in interstellar space within our galaxy is roughly 1 atom per cubic centimeter. The air around you right now contains approximately 27 billion molecules per cubic centimeter. Interstellar space is as close to a perfect vacuum as the natural universe produces, and it looks like it. Traveling through it at 400,000 miles per hour, you would see the stars essentially fixed against the dark. They shift position very gradually due to parallax as you move through space, but over days and weeks, nothing moves in any way that registers as motion. There are no landmarks, no passing features, nothing that provides any perceptible sense of forward progress. The sun, which would have been the brightest object in your sky from launch, gradually fades. Within a few years of travel, even at relatively modest speeds, it would be indistinguishable to the naked eye from the other bright stars around it. Just one point of light among thousands, getting no brighter and no larger as you turn to look at it. The destination, on the other hand, would be getting only imperceptibly brighter and larger. At the speeds we currently achieve, a target 1 light year away would show essentially no change in apparent brightness for years or decades. The experience would be something like standing completely still in a vast, dark room where the walls are too far away to see and the light sources are too far away to appear to move. As speeds approach a meaningful fraction of light speed, the visual experience changes dramatically. A phenomenon called aberration begins to distort the apparent positions of stars. Stars in your forward direction seem to crowd together and shift toward blue as their light is compressed by your approach. Stars behind you shift toward red and spread toward the edges of your vision. The physics behind this is the same Doppler effect that makes an ambulance siren sound higher pitched when it's approaching you and lower when it's moving away, applied to light instead of sound. At 10% of light speed, the aberration is subtle but visible with instruments. At 50%, the forward sky takes on a noticeably blue-white quality with stars clustering toward your direction of travel, while the aft sky grows redder and sparsely populated. At 90% of light speed, the entire star field compresses into a bright, dense ring surrounding your forward direction, with relative darkness both ahead and behind, and a thin, blue-white halo of blue-shifted light marking the boundary of your motion through the cosmos. The cosmic microwave background radiation, the ancient afterglow of the Big Bang that fills all of space with a faint thermal glow, would also undergo this shift, being blue shifted in the forward direction to become more energetic and visible, adding to the unusual quality of the view. At near light speed velocities, this radiation intensifies enough in the forward direction that it becomes a concern for astronaut radiation exposure, adding to the particle rain from the interstellar medium itself. Because at those speeds, the interstellar medium, that near-perfect vacuum of 1 atom per cubic centimeter, stops being negligible. Each hydrogen atom in your path, which at conventional spacecraft speeds you would sail through without any meaningful effect, hits the spacecraft with the kinetic energy of a fast-moving particle. At 90% of light speed, the accumulated effect of these collisions produces significant radiation and erosion at the forward surfaces of the spacecraft. At 99%, it becomes a serious engineering challenge requiring substantial forward shielding, specifically designed to handle this relativistic particle rain. Proposals for high-speed interstellar probes typically include some form of sacrificial leading shield or protective geometry to manage this. The silence and emptiness of the journey at any speed are part of what makes the prospect so philosophically significant to people who think about it carefully. The average distance between stars in our part of the galaxy is about 4 to 5 light years. The material between them, the gas, the dust, the magnetic fields, the occasional comet and rogue planet, is so diffuse that it is, for all practical purposes, nothing. Crossing that nothing intentionally, with purpose and instruments and a reason to arrive, is a different kind of act than anything our species has done before. Every other journey in human history has been made through environments that were, in some fundamental sense, part of the same world. An interstellar voyage crosses from one world to another through a gap so vast that our entire civilization fits inside it many thousands of times over. It's not just a trip, it's an entirely different category of thing. What the coming decades might actually deliver. Grounding all of this in what's actually likely to happen over the next century or so requires distinguishing between technologies at different stages of maturity and being honest about what we know versus what we're extrapolating. In the near term, the next few decades, the most important advances for interstellar capability are probably not going to look dramatic from the outside. They'll show up in materials, science papers, in propulsion test reports, in the performance specifications of deep space probes that don't make mainstream headlines. Better sail materials will improve the performance envelope for laser-driven concepts. More efficient ion drives will extend the reach of robotic missions deeper into the outer solar system and reduce transit times to the outer planets significantly. Compact nuclear reactors for spacecraft power being actively developed through NASA programs, including Kilopower and the Fission Surface Power Project, which aims to provide tens of kilowatts of electrical power from reactors small enough to fly on spacecraft, will enable propulsion and life support systems that don't depend on proximity to the Sun. These are the enabling technologies, the ones that make everything else possible, and they're being developed right now for purposes that have nothing to do with interstellar travel. The mid to late part of this century is where the picture becomes genuinely interesting for robotic exploration. If laser sail technology matures along the trajectory that Breakthrough Starshot outlined, this period could see the launch of the first genuine interstellar probes, gram-scale spacecraft pushed to several percent of light speed by ground-based laser arrays, crossing 1 light year in a decade or two before continuing toward the nearest stars. A mission targeting Proxima Centauri, launched in the 2060s or 2070s, could return data from another solar system before the end of the century. That's a striking possibility to sit with. People alive today could see the first direct images taken by a human-made object from another star system. The significance of that first mission would extend beyond the data it returns. Every time humanity has sent a probe to a genuinely new environment, to the outer planets, past Pluto, into interstellar space, it has returned discoveries that changed what we thought we knew. Voyager revealed complex structures at the boundary of the heliosphere that theorists hadn't predicted. New Horizons showed Pluto to be a geologically dynamic world with mountain ranges and plains of nitrogen ice, nothing like the featureless ball most scientists expected. An interstellar probe, even a flyby lasting only hours, would almost certainly show us something unexpected about Proxima Centauri and its planets. And those surprises would reshape the scientific questions driving the next generation of missions. The third decade of this century has already brought meaningful progress on nuclear fusion. The National Ignition Facility at Lawrence Livermore National Laboratory achieved fusion ignition for the first time in December 2022, producing more energy from fusion than the laser energy deposited into the target. Commercial ventures including Commonwealth Fusion Systems, Helion Energy, and others are pursuing compact reactor designs with aggressive timelines. If sustained fusion power becomes an operating technology on Earth within the next 30 to 50 years, which increasing numbers of fusion researchers now believe is achievable, the implications for spacecraft propulsion are significant. Fusion power plants capable of generating gigawatts of electricity would also be capable, in principle, of powering the kind of ion or plasma drives that could push spacecraft to meaningful fractions of a percent of the speed of light, and eventually to the few percent velocities that nuclear pulse propulsion designs like Daedalus projected. A fusion-powered probe at 10 to 12% of light speed within the envelope that Project Daedalus analyzed in detail would cross 1 light-year in 8 to 10 years. Proxima Centauri would be a 40-year mission. These numbers, while still demanding, start to feel achievable on human timescales, within the budget and political will of a civilization that decides this is worth doing. Crewed interstellar missions are harder to project and require more honest caution. In addition to propulsion, they require simultaneously solving radiation shielding adequate for years in deep space, closed-loop life support reliable for decades, the biological and psychological management of extreme long-duration isolation, and some means of making the subjective duration of the journey survivable, whether through hibernation, rotation, or other approaches. None of these problems violate known physics. None of them are obviously unsolvable, but none of them have clear solutions on any near-term horizon, and none of them can be addressed in isolation. They all have to work together simultaneously for the full duration of the mission. A crewed mission that crosses 1 light-year in a human lifetime probably requires technology that doesn't exist yet and won't exist for another 100 to 300 years, depending on how the relevant research trajectories develop. That's not a pessimistic conclusion. 300 years is a small fraction of the time our species has existed, and a tiny fraction of the time that life has existed on Earth. The relevant question isn't whether the problems are hard. They clearly are. The relevant question is whether the direction is right, and by every measure available to us, it is. The bigger picture, the question of how long it takes to travel 1 light-year is, at its core, a question about where we are in the long arc of becoming something more than a single-planet species. And when you step back from the specific numbers, the picture is more nuanced than either pure optimism or pure despair would suggest. The distances are genuinely extreme. The physics is genuinely challenging. The human biological limitations are genuinely serious. A traveler at our current best speed would take over 1,000 years to cross 1 light-year, and our nearest stellar neighbor is 4 times further than that. The universe is not configured to make this easy, and nothing in our near-term technological trajectory is going to change that fundamental fact. At the same time, something called the Fermi paradox sits in the background of every serious conversation about interstellar travel. Enrico Fermi, the physicist, observed informally in 1950 that in a universe as large and old as ours, with so many potentially habitable planets, the apparent absence of detectable intelligent life beyond Earth is puzzling, because if intelligent life were common, and if any of it had developed interstellar travel capability even once, the galaxy should by now be saturated with evidence of it. And yet the sky is quiet. One resolution to the Fermi paradox is that interstellar distances are simply too extreme for any civilization to cross routinely, and so intelligence exists in pockets scattered across the galaxy that never make contact with each other. The numbers we've worked through today are at least consistent with that picture. If the minimum meaningful interstellar crossing time is measured in decades even for advanced technology, and if getting there requires solving problems of the scale we've discussed, then perhaps the silence is simply a function of the universe's geometry rather than the absence of company. Or perhaps not. The Fermi paradox has many proposed resolutions, and the evidence isn't strong enough to choose decisively between them. What it does suggest is that interstellar travel, if it's ever achieved, will represent something genuinely exceptional, not just a technical achievement, but a threshold. It's worth spending a moment on why that threshold matters beyond the scientific and exploratory arguments. Earth is not a permanent home for our descendants. On the scale of billions of years, the sun will change. It will gradually brighten over millions of years, eventually making Earth's surface uninhabitable long before it reaches old age. The time frame for Earth becoming too hot for complex life due to increasing solar luminosity is estimated at around 1 billion years, a long time by human reckoning, but short by the standards of the universe's age. On much shorter timescales, millions of years rather than billions, the probability of extinction-level events from large asteroid impacts, nearby supernovae, or catastrophic volcanic episodes is non-zero. The geological record is clear on this point. Mass extinctions have happened before on Earth, and there's no reason to assume they won't happen again. A species that exists only on one world is a species with one point of failure. The long-term persistence of life that originated on Earth, whether that means future humans, something descended from humans, or simply the biological lineages and ecosystems we carry with us, probably depends at some point on becoming an interstellar species. That isn't an urgent problem in any near-term sense, and it would be wrong to frame it as a reason for immediate alarm. It's a context that changes how you think about the research being done today and about its ultimate significance. Every paper on sail materials, every design study for nuclear pulse propulsion, every advance in compact fusion technology, these are not just academic exercises or engineering curiosities. They're early contributions to a capability that may ultimately matter at a level that dwarfs any other endeavor humanity is currently undertaking. The first person to demonstrate sustained fusion ignition in a laboratory didn't know they were working on interstellar propulsion. They were working on clean energy. But the steps connect. The history of technology gives a useful frame for thinking about progress on this scale. In 1900, controlled powered flight had never been achieved. In 1903, the Wright brothers' first successful flight lasted 12 seconds and covered 120 feet. By 1969, 66 years later, a human being stood on the moon, 239,000 miles from Earth. The jump seems staggering in retrospect, but it was built from one development on top of another. The Wright brothers led to military aviation in the First World War, which led to commercial aviation, which led to jet engines, which led to rockets, which led to satellites, which led to the spacecraft that finally landed on the moon. Each step enabled the next. None of them, in isolation, looked like it was leading to the moon, but the chain connects. That progression from 120 feet to 239,000 miles in 66 years represents an increase in range of about 2 billion. The gap we need to close for interstellar travel from Parker Solar Probe speeds to 10% of light speed is a factor of about 100,000. That's a smaller improvement in relative terms than what aviation achieved between 1903 and 1969. The difference is that rocket propulsion appears to be harder to scale than aviation was. The physics of chemical propulsion hits its limits before we reach interstellar velocities, while aviation was able to keep improving within a single propulsion paradigm for decades. Closing the interstellar gap requires a genuine paradigm shift, not just optimization within an existing approach. That makes the history of aviation an imperfect analogy, but not a useless one. The pattern of progress, adjacent technology opening unexpected doors, incremental advances enabling a revolutionary leaps, tends to repeat across the history of engineering. There is also the role of robotic exploration to consider, which is often undervalued in these conversations because it lacks the drama of crewed missions. The first interstellar crossing, whenever it happens, will almost certainly be unmanned. A gram-scale nanocraft reaching another star system would be, by any honest measure, one of the most significant events in the history of scientific exploration. We would receive, for the first time, direct observational data from another solar system, images of planets at close range, magnetic field readings, measurements of particle environments, spectroscopic data on any atmospheres present. We would know, with the precision of direct observation, rather than telescope inference, what another star system actually looks like from nearby. That mission would also teach us things we can't anticipate. JWST's first images of exoplanet atmospheres have already begun revealing chemical compositions that don't fit simple models. An interstellar probe flying through a neighboring solar system would operate in an environment no instrument has ever visited, and the probability that it would show us something we didn't predict is essentially certain. The only question is what kind of surprise it will be. These discoveries matter not just because they're interesting in themselves, but because they drive the next round of engineering. Each time we discover something unexpected in a new environment, we design better instruments for the next mission, and the instruments designed for the next mission push materials, science and miniaturization forward in ways that feed back into propulsion research, power systems, and communication technology. The robotic program and the underlying technology program reinforce each other. The broader point is that the question of how long it takes to travel 1 light year doesn't have a single answer. It has a range of answers that spans from longer than recorded history to a few years, depending on what technology you use. That range itself tells you something important. It tells you that interstellar travel is not categorically impossible. It sits within the space of physical law. It is constrained by engineering rather than by the nature of reality. And engineering problems, given sufficient time and effort, tend to get solved. The fact that the best answer we have today is around 1,600 years with a Parker Solar Probe class spacecraft, but that a theoretically sound design based on lasers could reduce that to 5 years, is not a statement about the limits of the universe. It's a statement about where we are right now in the development of the relevant technologies. Those technologies will not stay where they are. The honest summary is this: with current technology, crossing 1 light year takes around 1,600 years. With near-future laser sail technology, a robotic probe could do it in roughly 5 to 10 years. With nuclear fusion propulsion that exists on paper and may exist in hardware within the next century, a spacecraft of real substance could make the crossing in 8 to 20 years. with antimatter propulsion, which we cannot currently manufacture at relevant scales, 1 to 2 years, with warp drives or wormholes, which remain mathematically consistent but practically far beyond reach, the crossing becomes effectively instantaneous. Each step in that progression is more technically demanding than the last, and each is closer to what the universe actually permits. The trajectory is real, and it's moving in one direction. Every generation of spacecraft has been faster than the last. Every decade of physics has refined our understanding of what the universe allows. Every year, the tools available to researchers working on these problems become more capable. The stars are not getting closer, but we are, in the only way that actually matters, getting better at going toward them. 1 light year is a very long way. It is also, in the full sweep of what the universe contains, an extraordinarily short distance, less than a quarter of the way to our nearest stellar neighbor. A small step in the galaxy that spans 100,000 light years, itself one of several 100 billion galaxies in the observable universe. The fact that we are already designing the tools that might one day cross that first light year, already running the experiments, building the materials, writing the physics, debating the engineering, is remarkable in itself. The question of how long it would take is real and hard, and the honest answers are mostly sobering in the near term. But the direction is clear and the work is underway, and that combination has historically been enough. So the next time someone throws out 1 light year like it's a casual unit of measurement, you'll know what it actually means, and you'll have a sense of just how extraordinary it would be to cross it. If you made it this far, thank you for watching. If you found this interesting, subscribing genuinely helps. It tells the algorithm that this kind of content is worth putting in front of more people, and it means we can keep making videos like this one. There's a lot more where this came from: black holes, dark matter, the fate of the universe, the search for life beyond Earth. Hit subscribe and you won't miss any of it.